This, we review more or less everything that we have seen. We will review more or less everything. You have a standard Murchison interferometer. The only different thing with respect to what you have seen is that we use a diodo laser, a DFB laser, distributed feedback, the DFB stands for that emit with a wavelength of 1500 nanometer, with a power, the emitted power of 10 milliwatt, and with a line width of 300 kilohertz. This is an ideal DFB laser because, as we have seen, this width is quite difficult to achieve, even with a distributed feedback laser. And then we have the usual configuration, in which we have a beam splitter with the 50% ratio. So 50% of light is transmitted and 50% of light is reflected toward what we have the fixed mirror, and then here you have the move. Instead of a mirror, you have, let's say, a corner cube that is mounted over a loudspeaker. Okay, so you have something like this.
Yeah.
Okay.
Of course.
Then you have a composition of the two electric fields, the measuring one and the reference one. Then you go onto a photodiode. You get the photodetected current. Okay. And then you transform the photodetected current into a voltage using a transimpedance amplifier. Okay?
Professor?
Then you get what? A photodetected voltage. Okay? Do you know what is a transimpedance amplifier? Yes? No? Okay, but more in general, when you have a photodetector, you can build this very easy scheme. You make use of an operational amplifier with a simple resistance in feedback. Then if you have the photodetected current, okay, you develop here a photodetected tension voltage, okay? This is easy. And in this condition, what you have that the photodetected voltage is equal to minus R multiplied by EPH, okay? This is because here you have the virtual short circuit or ground, so you have 0 voltage here, so all the current goes into the resistance, and then you have the minus sign here. Okay? So this is what happens to transform, what you have to do to transform current into voltage, one of the possibilities, of course. Then you have also this quantity. This distance is called LR. Then you have that this distance is called L2. Then you have Lm. And then you have L1. Okay. Okay. The responsivity of the photodiode is 0.5 ampere over watt. The loudspeaker is, the target is a loudspeaker. Now this loudspeaker is excited with a sinusoidal signal with a frequency. So let's talk of the frequency of the loudspeaker is 100 Hertz. The voltage that you apply to the loudspeaker is 5 volts peak-to-peak value. Okay. And you know that to transform, let's say, voltage into displacement, the sensibility of the loudspeaker in displacement is, let's call it KL, or better, SL. And this quantity is given by 2.635 micrometer per voltage. So what does it mean? That if you apply 1 voltage to the loudspeaker, it moves up to 0.635 micrometer. Then the other data are the reference path is equal to 1 meter, and the measuring path or the measuring arm is equal to 1 meter. The reference arm is equal to 0.5 meter. Okay? Okay, first question of the exercise. You need to evaluate what is the maximum value and the minimum value of power that comes onto the photodiode. So, P max and P min. Okay? So to answer this, you have to recall that onto the photodiode comes the summation of the reference and measuring field. Okay? And then the power is related, for the, let's say, the power in general is related to what? M, okay, plus E R squared. Okay? This is what happens. So what does it mean? That if you recall our first lecture about interferometry, what you have that the maximum power is given by what? Let's call it the power, let's say P1 plus P2, okay, plus the squared value of the product of the two. Then you have that the lowest possible value, or the minimum one, is given again by P1 plus P2 minus P1, P2. Okay, this is why. Because in general, if you follow this equation, the power is given by P1 plus P2. These are the contribution of the two fields. Okay. And then what you have plus, sorry, there is a sign. There is a sign here. There is a 2 here, sorry. I was forgetting the 2. And 2. Okay. P1 multiplied by P2 multiplied by cos of what? The interferometric phase. So you have 2K multiplied by Lm. In this case, you have movement of the loudspeaker, so let's say that Lm is time dependent. Okay? And then here you have the subtraction of the reference path that instead is fixed. Okay? So, since you want the maximum and the minimum, then the maximum occurs when the phase, the interferometric phase, is equal to 0 or multiple of 0. So, multiple of 2 pi, that is better. And then, of course, the minimum is when the cosine is minus 1. Okay? So we have multiple of alpha pi, or just pi. Okay? Then, how you can evaluate the two values of P1 and P2. So, for example, let's suppose that P1 is related to the measuring path. Okay? So what we have? We have P0 that is emitted from the laser. Then you have half of the power that is transmitted toward the loudspeaker. Okay? Then we have 5 milliwatts here. And then coming back, sorry, there is another point. I have to tell you that the reflectivity of the fixed mirror is 90%. So the reflectivity of the reference mirror is 90%, and the reflectivity of the measuring mirror is 5%. Okay? So, P1. I have got P0 over 2. This value is what is transmitted by the beam splitter. Then I have to multiply by 5 over 100 because of this low value of reflectivity. Then I'm coming back toward the beam splitter, and then I have reflection of, again, half of the power. So again, I have another factor of 1 over 2, and then what happens? That this is equal to P0 multiplied by 5 over 400. And this should be equal to 0.125 milliwatts. Okay? We can apply the same reasoning for evaluating the power, the second value of power, that is the one that comes from the reference path. In this case, we have more or less the same situation for the first reflection. Again, half of the power is reflected. Then 90% of power is reflected back toward the splitter. And then we have again a loss of 2 because we have transmission by the loudspeaker. So what we get here is 0 multiplied by 90 divided by 400. Okay? And this is equal to 2.25 milliwatts. Okay? So we are ready to evaluate maximum and minimum power. In particular, what you get? You get 3.435 milliwatts for the maximum, and you get 1.314 milliwatt for the lower. Okay?
Second half is for again being reflected by the beam splitter?
Yes, because you have, independently of the two signals, you have, for example, look at this path. You have one reflection, so you lose half of the power. Then you have 90% of reflection, and then you have another loss of a factor of 2 because you have transmission. And again, the ratio is 50-50. Okay, so this is the first calculation. You just always remember that this is what happened because of this fact. Okay? Then, let's see. Let's seal out this. Now this is useful. And okay, the second question is you have to write explicitly the photodetected voltage, the equation, the relation that tells you how the photodetected voltage changes with time. So, in a very easy way, we have seen that the photodetected voltage is given by minus R, where R is the resistance of the transimpedance amplifier, okay, the feedback resistance of the transimpedance amplifier, and then this is multiplied by
The voltage of
the photodetected current that is dependent on time. So, since the photodetected current is related to the power, then you can continue, and then you have minus R, then sigma, that is the responsivity of the photodiode, and this is multiplied by the optical power, the instantaneous optical power. Okay? So to get the correct expression of the photodetected voltage, you just have to explicitly write what is this term, LMT. Because what you know is that you are driving a loudspeaker with a sinusoidal voltage, okay, with a particular frequency. So what does it mean? That, let's say, the time varying, let's say, part of the measuring part is given by S0, where S0 is the amplitude of displacement of the loudspeaker, multiplied by what? By sin of 2 pi f loudspeaker multiplied by t. Okay? And in particular, LMT is given by what? By the starting value, that I have already told you what is the value, then plus S0 sin 2 pi f L t. Okay? So that I'm not rewriting everything, but the important thing is just to concentrate on the interferometric phase. So let's call this quantity the interferometric phase. And then what we have? 2K Lm minus Lr plus 2K multiplied by what? S0 sin 2 pi f loudspeaker t. So you have a fixed phase, okay, and then you have a time varying phase. This is the quantity. This is the part of the phase that will generate interferometric fringes or the interferometric signal. Okay, so this is the important point. But never forget that you have also the constant term. Okay, so these are always present. Okay, and in particular, you can choose the value of, let's say, the starting value of Lm with respect to the one of Lr, for example, to work at the alpha fringe working point that you have already seen last time. Okay, so these two terms are important. So of course, the only term that is important to evaluate, let's say, interferometric things is this one. Okay, but with this term you can change the working point of the interferometer. So Never forget this. Okay? Okay. Okay, there was also another question. The question is, what are now the minimum and maximum value of the photodetected voltage? Photodetected maximum and photodetected minimum. You have to pay attention to answer to this question because the calculus is, of course, definitely easy, but you never to forget the minus sign, okay? Because the maximum value of the photodetected voltage is related to sigma. Okay, this is correct. R is the feedback resistance, and then you have the minimum value of power, and the maximum is, sorry, the minimum value of the photodetected voltage is again sigma R P max. Okay. Well, to be honest, this is an open question because someone can say, okay, the usual transimpedance amplifier is the one that you showed, but you can also use this configuration. So it is quite, let's say, popular. You can also use this simple configuration. You have, again, of course, the operational amplifier. Then, of course, again, the feedback resistance. Here you are measuring the photodetected voltage, okay? But you put the photodetector in a short circuit. So, you put it here, okay? What is the great difference between this configuration and the one that we have seen? That now the signal is positive because EPH, the photodetected current, goes in this direction, okay? So that an increase in the photodetected current causes an increase in the photodetected voltage, okay? What is the great difference? Because it seems easier or better to use this configuration. Because for an increase in photodetected current, you have an increase in voltage. So you don't have the minus sign. But what is the real, let's say, drawback of this configuration?
The diode is not polarized.
Yes, the diode is not polarized. Or this is a scheme that is, let's say, a dark current concealing scheme. Okay, because of course, if the photodetector, in this case the photodiode, has 0 voltage between the anode and cathode, of course, the dark current is 0. Okay, so you have a good point, dark current is 0, but you have a drawback because the polarization of this photodiode is not polarized in inverse voltage. Okay, so you just have to understand what is better for you, for your application. In this case, since now the photodetector, let's call it starret, this is given by plus sigma multiplied by R multiplied by EPH. Okay? So EPH remains the same. It does not change. But if you use this configuration, of course, what you get that the maximum value of the photodetected voltage is related to the maximum value of power. Sorry. This is correct. And instead, if you talk of power, this is related to max. And the minimum of the photodetected voltage is sigma R P min, okay? So both of the solution can be accepted. It is important that you say what is the scheme that you are going to use. Okay? Okay. Okay. Okay, third question. Now, what is the resolution of this instrument? Okay, so again, this is an open question because your exercise does not tell anything about the analysis of what you do of the photodetected voltage. Okay, you can decide what you are going to do of the voltage. So we can go with the easiest possible solution or answer, that is, since this is a Murchison interferometer, the resolution is simply given by half of the wavelength. This is the simplest possible solution. Because what you say, okay, I measure the displacement of the loudspeaker in terms of an incremental measurement, a digital one, and I do this measurement measuring the period, let's say, in the photodetected voltage. Simplest as possible. Of course, another possible solution could be, no, I want to measure not just the period, but the upgoing and downgoing jump into a squared wave. Because remember that you can always get this, you always get this. Let's say this is the modulus of the photodetected voltage, so whatever the the configuration of the transimpedance amplifier, the signal is always the same, and you have let's call the mean value, and then in this condition, okay, so you can count just fringes, so obtaining one count for each period, or you can say, okay, I transform this signal into a squared wave, then I do the derivative, and then I can always count also for the minus jump. So I can count also for 2 points for each 2 pi. In this case, okay, no, I'm talking of time, but this is correct. I can always use, let's say, the interferometric phase. In this case, it's correct to talk of 2 pi. Okay. So let's go with the first solution. So let's say that our resolution is lambda 0 over 2. Okay. The second point is of the same question. You have to evaluate what is the interferometric phase change for a full displacement of the loudspeaker. Okay. Now I recall that the, let's say, movement or displacement of the loudspeaker can be written in this way. Okay? So a full displacement of the loudspeaker, full displacement of the loudspeaker is equal to 2S0. Okay? So that, let's say, the variation of the interferometric phase that is related to a full displacement of the loudspeaker is simply given by 2K multiplied by 2S0. Okay? And in particular, this is equal to (106.76 radian). Okay. Calculations are very, very simple. Okay. The only thing that you have to pay attention to is what is the value of is 0. Okay? Because the data of the exercise tell you that gives you the peak-to-peak voltage of the sinusoidal voltage that is applied to the loudspeaker. Okay? So, what does it mean? That is zero, that is the amplitude in displacement of the oscillation of the loudspeaker, is given by what? The peak-to-peak voltage divided by 2, never forget this, multiplied by the sensitivity or the sensitivity of the loudspeaker. So in particular, you get this is equal to, this is 5 divided by 2 multiplied by 2.635. Okay, these are voltage and these are micrometer over voltage. So what you get is 6.5875 micrometer. Okay? Don't forget these two. This is the point. Okay, now another question. With this phase, how many interferometric fringes I will see onto the oscilloscope, for example, or if I try to look at the photodetected current or voltage?